We will continue on the learning algorithms. So, the next classifier we are going to study is the decision tree classifier. So, what we have is a graph here, a graph which consists of nodes and edges, and it is such that there is no cycle. So, what you get is a tree basically. And it is a rooted tree which we are talking about. Okay. So, in every node you have a condition on a particular feature. So, these nodes are known as the decision nodes, and from that, depending on the outcome, you have the outgoing edges. Okay. So, for example, you can say one of the nodes can have something like, say, if feature f1 is less than say 4, and you can have two outgoing edges saying yes and no. So, if it is less than 4, it goes along the yes, and if it is greater than 4, it goes along the no. You could also have more than two outcomes from a node. So, it has two or more outgoing edges depending on the outcomes that you are going to get, and the leaf node that you have gives you the class labels. And if you take a path, the path will start from the root node and go to a leaf node. So, you have a path, and each path will give a rule, okay? And the consequent of that rule is the class label which is there at the leaf node basically. So, it is a tree with the non-leaf or internal nodes being associated with a decision, and the leaf nodes are associated with an outcome or a class label basically. So, in the internal node it will test one or more attribute. Okay. So, it is possible it is just one attribute, it could be more than one attribute which is being tested at a node, and depending on the test it takes one of the output branches which go out from it. And these links are mutually distinct and collectively exhaustive. This is because if you have the feature taking a certain value, it should be going only on one of the output branches. So, that is why they are mutually distinct and collectively exhaustive, because if you have the feature taking a value and it does not come in any of the branches which are coming out, that is not correct, right. So, it has to be collectively exhaustive. So, for a value you follow only one link and all possibilities are taken care of. So, whatever the feature value may be, there will be one link along which it goes. So, it could be a decision tree. Of course, here we talk about making a decision on which class it belongs to, but it can be used for choosing between various courses of action. So, for example, if we take this particular example here. So, we have 4 coins A, B, C and D. The three coins are of equal weight and one coin is heavier. Find the heavier coin. So, how do we find this heavier coin? So, we consider 4 coins A, B, C and D. So, this decision tree tells you how to solve this problem or find the solution to this problem. So, A plus B is compared with C plus D. Is A plus B greater than C plus D? If it is, then you compare A and B, and if A is greater than B, A will be the heaviest. If it is not, B will be the heaviest. Otherwise, you come along this branch and you check if C is greater than D. If it is yes, then C is the heaviest, otherwise D is the heaviest. So, this is an example of a decision tree being used to solve a problem, right. So, what are the things that characteristics we can see of the decision tree here? The 4 leaf nodes correspond to the 4 outcomes. So, the leaf nodes always are the outcomes that you are getting, and the non-terminal or the internal nodes are the decision nodes. And if you take a path from the root to the leaf, it corresponds to one rule. Okay. For example, if we consider this rule, we can say if A plus B is greater than C plus D and A is greater than B, then the heaviest one is A. So, that forms one rule. So, any path from the root to the leaf forms a rule. So, let us take another example of a pattern classification problem. So, here we are talking about different animals. So, let us say these are the classes that we are having, and each one has these description. Okay. So, a cow has 4 legs, it has horns, the size is medium, it is white, does not have a beak, and this is the sound that it makes, etc. And if we take a mouse, it has 4 legs, it does not have horns, it is small, it is black, it does not have a beak, and it squeaks, etc. So, this is the description that we have, and this is a decision tree that we have made. Okay. So, what you can check is number of legs, is it 2 or 4, right. So, if it is 2, then you check whether it has a beak. Okay. If it has a beak, then you check the color, and depending on the color you can get the leaf node which tells you which animal it is, right. And if it does not have a beak, then you say it is a human, and if it is 4 legs, then you check whether it has horns, yes, no, right. If it is yes, then you look at the size, if it is no, then again look at the size, and you can find which animal that you are looking for. Okay. So, this is a decision tree which has been created. So, let us say some of the characteristics of a decision tree used for classification. Okay. The class labels are associated with the leaf node, and root to leaf represents a rule. So, that we have seen. Every internal node involves making a decision. Irrelevant features do not occur in the decision tree. So, let us see how this happens. So, here we have actually a feature which gives the sound made by the various animals, right. But we have not used that anywhere in this decision tree. Okay. So, we can say that it is a redundant feature, irrelevant feature, and both numerical and categorical features can be used. So, here we have used the numerical feature 2 and 4, number of legs, and we have used categorical feature color, okay, size. So, and we have used Boolean feature yes, no, right. So, we have used all type of different features here, okay, which you can't say the same thing is possible with say something like nearest neighbor. Like nearest neighbor, all the features are actually numerical. Okay, you cannot have categorical features, etc. Right? And the tree can be binary or non-binary. Okay, so we can see here that this is a non-binary tree because some of them have 3 outcomes, etc. Right? So, it could be either binary or non-binary. A set of patterns is associated with each node. So, what happens is you have your data set, right, and the data set you have a training data set and you are going to check number of legs, right. So, associated with the root node will be the entire data set that you have. Now, when you check number of legs, all those patterns which come in number of legs equal to 2 will come this way and number of legs equal to 4 will come this way. So, what you find is you will find a subset of those patterns which are associated with this node, and you find a subset of these patterns which are associated with this node. And similarly, as you go down, the subset becomes smaller and smaller. The rules are simple and easy to understand. So, these are some observations. So, now we need to see how do we construct the decision tree. So, we have a data set and the data set tells you examples, okay, of every class. So, we have a training data set. How do we use the training data set to induce your decision tree? Okay. So, what you have to do is at every node you have to use the best attribute to use. Okay. So, we are assuming here that only one attribute is used per node. Okay. So, when we are going to get the root node here, okay, and we are going to use a particular feature, say fi, right, which feature do we use there? Okay, that is what we need to see, which is the best feature to use. So, once we use that feature, you will get branches like this. What is the feature that you are going to use here? What is the feature that you are going to use here, right? So, that is what is going to change basically, and we need to see how we go about doing this. Okay, so, what we use is we use what is called the measure of impurity. How do we calculate this measure of impurity? So, IN is your it is called the entropy impurity. So, you are using the entropy or the information impurity formula here, right. So, you are saying basically that if there are say j outcomes, p of omega j log to base to p of omega j is basically the thing, where p of omega j gives you the fraction of patterns of category omega j. Okay, so, this gives you your category. So, suppose you have two classes, okay, and you have p of omega j to be equal to 0.5, you will get minus 0.5 log 0.5 minus 0.5 log 0.5, which is 1, right, which means it is going equally in the two branches. If all the patterns go along one branch, okay, then you find that you are going to get here 1 log 1 minus 1 log 1 minus 0 log 0. So, you will get your IN equal to 0. Now, if there are 10 patterns which are split into 3 branches with 4, 5 and 3, you are going to get minus 0.4 log 0.4 minus 0.5 log 0.5 minus 0.1 log 0.1, which will be 1.36. So, this is known as the entropy or information impurity. Now, let us look at another such measure. It is called the variance impurity. Here you are taking the multiplication of p of omega 1 and p of omega 2. So, suppose both of them are 0.5 like we saw in the previous case, your IN will be 0.25. If all the patterns go along one branch, you are going to get IN equal to 0. Now, if you have more than 2 categories, then you have to use this formula here, okay, which is called the Gini impurity. So, that will be IN will be equal to sigma p omega I p omega j, where I is not equal to j, right. So, if you have 3 categories, p omega 1 p omega 2 plus p omega 2 p omega 3 plus p omega 3 p omega 1. So, that type of thing. So, it takes all combinations of these 3, but you can also write it as half into 1 minus sigma p squared omega j. So, for the 3 categories we spoke of earlier, you will get half into 1 minus 0.4 squared minus 0.5 squared minus 0.1 squared, which is 0.29. The third type of impurity we talk about is called the misclassification impurity. So, here you take the maximum of the p of omega j. So, when it is 0.5, your IN will be 0.5. When it is 1 and 0, you will get IN is 0, and if you have 3 categories you will get 1 minus max of these, which is 0.5. So, again you will get 0.5. So, these are 3 different misclassification impurities which we can use to choose the attribute at a particular point. So, let us see how we go about doing this. Okay. How do we choose an attribute here? Okay. So, we found the IN, right. So, you have to find the delta IN, which is actually the drop in impurity, and it is also called the gain at a node n. Okay. So, suppose you find this what you are getting here is basically the IN over here, and suppose you have a left branch and the right branch. We are talking about INL and INR here. Okay, so, the drop in impurity at this particular node is going to be IN, the IN there, minus the number of the percentage of patterns that go along the left branch into INL minus PR into INR. So, this is for 2 branches. If there are more than 2 branches, you use this particular formula. So, then what you do is you find this delta IN for every feature, and the feature which has the maximum delta IN, okay, that is the one that you are going to use, you choose at a particular point. So, here is an example where you have 40 going in the left branch of class 1, 0 in the right branch of class 1. For class 2 you have 10 going in the left branch, 20 going in the right branch, and for the class 3 you have 10 going in the left branch and 20 going in the right branch. This is the total 40 into 30 plus 30, which is 100. So, how do we find the impurity? So, what we are trying to do IN here is what we are so we are trying to find the IN which comes here, right. So, we have altogether 100 which go into 40 here, 30 here and 30, sorry, it consists of 40, 30, 30 of each class basically. Okay. So, you find your IN like this, okay, which is 1.38. Now, entropy of the left branch. Okay, so, what you are getting as output is 2 branches. So, the left branch will be INL, okay, that is a left branch, is minus 40 by 60, okay, because total is 60. This is 10 by 60, this is 10 by 60. So, this will be the value, and entropy of right branch will be 0 by 40, 20 by 40, 20 by 40. So, this is the right branch entropy that you are getting here, okay. And your IN will be 1.38 minus you have 60 going along the left branch. So, 60 by 100 into 1.25 minus 40 by 100 into 1. So, this gives you your delta IN, and if you use variance impurity you are going to use this. Okay, so, half of 1 minus 0.4 squared minus 0.3 squared minus 0.3 squared. Similarly, you can get impurity here, and I of NR you can get, and then the delta IN. If you are using misclassification impurity, you are taking the max of these 3, right, into the 1 minus basically, right. So, you are again getting 0.6 and you can, all the minus has been left out. So, just assume there is a minus there. So, here also we are going to do the same thing and we can get the delta in over here. Okay. So, this is how you do that. Now, what are the type of splits that we can have? Okay. So, one split is what is called the axis parallel split. So, in the case of axis parallel split, you are using only one feature at a time. So, you are going to have a node which has a decision which says f I. So, f 1 greater than a, yes or no, right, that will be the output. So, this is what is called the axis parallel split. So, if you have an axis parallel split, okay, so here we have actually A and B. Okay. So, this is the decision tree you are going to get. F 1 is f 1 greater than 4. If it is yes, if it is no, then it is x 1 to x 4, okay, which is belongs to class X. Otherwise, if you take f 2 greater than 4, yes, no. If it is yes, it belongs to class X, otherwise it belongs to class O. Now, you can also have an oblique split, right. Suppose we take an oblique split like this, such that all the patterns belonging to X come on that side, all the patterns belonging to O come on this side. We can take these patterns which are there at the boundary and we can use them to find the equation of this line. So, once we find the equation of this line, so if we get this line, then it is easy because we can say that whatever comes to the left of this line is X and whatever comes to the right of this line is O. So, your decision tree actually is going to become much simpler. Only thing is getting the split is going to be a little more difficult. So, what we are getting is something like this. So, you are getting an equation here which says is f 1 minus f 2 less than 2, yes or no. If it is yes, then you get X, if it is no, you get O. So, you can see that your decision tree becomes much simpler by using the oblique split. Only thing is it may be a little more difficult to get the oblique split than the axis parallel split. Okay. So, the earlier work which we spoke of actually shows that we are using only the axis parallel split. So, we are assuming that every node there is only one feature which is being taken at a time. So, we are using the axis parallel split. The third type of split is what is called the multivariate split. So, in the axis parallel split, we used a linear equation of this line, right. So, we used a 1 f 1 plus a 2 f 2 is equal to a naught, or in other words a 1 f 1 plus a 2 f 2 plus c equal to 0. Okay. So, that is the equation of this line which we are using. In the case of multivariate split, you are using a nonlinear combination of features. Okay. So, this becomes even more difficult and we will not talk about this case, but what you are getting basically is not a straight line, but you are getting some type of a nonlinear curve over there. Okay. So, here we are talking about one particular example. Okay. So, this is a very popular example which is used. So, we have 14 instances here. So, we have 4 features: outlook, temperature, humidity and wind, and outlook can take either sunny, forecast or rain, and temperature can take hot, mild or cool. Humidity can be high, normal, and wind can be weak or strong, and the class label that we get is either yes or no. Okay, so it is a Boolean or a binary classification. Either play tennis is yes or no. So, depending on all these features that we have, you have to decide whether to play tennis or not, depending on the weather that is there. So, this is the problem that we are actually working on. So, we can see basically that we have 14 values, and out of those 14 values 1, 2, 3, 4, 5. 5 of them give play tennis is equal to no, and 9 of them give play tennis is equal to yes. So, what we do basically is we need to find the impurity. So, the IN or the what you are starting with, right. So, we have 5 of play tennis equal to yes, and altogether we have 14. So, this will come to minus 5 by 14 log to base to 5 by 14 minus 9 by 14 log to base to. So, this would be your IN which you are starting with. Okay. Okay. So, now let us look at outlook. Okay. So, outlook, if you see, there are 3 things: sunny, overcast and rain. Okay. So, what you find in outlook is that in sunny there are 2 which gives play tennis as yes, and 3 which gives play tennis as no. Okay. So, we can calculate the entropy of that. Okay. And then if you take outlook, 4 of them give play tennis as yes and 0 give play tennis as no. So, we can find the entropy of that. And here 3 of them give play tennis as yes and 2 of them give play tennis as no. So, we can find the entropy of that. So, once we do this, we can combine these 3. Okay. So, how do we combine these 3? So, we get the gain of outlook, which will be 0.94. So, the 0.94 is this value here minus. So, here altogether there are 5 patterns in sunny. So, you get 5 by 14 into 0.97 minus there are 4 here, 4 by 14 into 0 minus 5 by 14 into 0.97. So, altogether you get 0.247, right. So, this is the gain for outlook. So, once we do outlook, we can do the same for humidity, wind, temperature, etc. Okay. So, once you do all that, you get the information gain for all of them, right. So, this is the gain for wind, etc., right. So, this is the values that we have. So, the gain for outlook is 0.247, the gain for humidity is 0.151 and the gain for temperature is 0.029. So, you can see outlook has the highest gain. So, whatever has the highest gain, you take that feature as the feature on which you are going to have the root node or the node at that particular point in time. So, once you do that, you are going to divide your data set into 3 parts. So, out of the 14, so let me go back here. So, out of the 14, since you have taken outlook, you have all the sunny ones 1, 2, 3, 4, 5. So, you have 5 patterns going along the sunny outcome, and you have the 4 going in the forecast, overcast, and you have 5 going in the rain. Okay. So, what happens is this data set actually reduces for each of these outcomes that we have, right. And then you take each of them separately and you decide, you do the same procedure again, okay, and you decide what is the next feature that you are going to find in each of these 3 branches, okay. And you keep doing that till you come to a place where all the patterns go along one of those paths and the other one will be 0, etc., right. So, when you keep doing this procedure, you are finally going to come to this. Okay. So, this is your decision tree for play tennis. So, you find if you take outlook as sunny and then you check humidity as high or normal, then you know that play tennis is no or yes. And if outlook is overcast, then play tennis is yes. If outlook is rain, you check the wind. If it is strong, then no play tennis. If it is weak, yes. So, this is your final decision tree that you are going to come to by doing this process over here. So, this is your final decision tree which you have got. Okay, so, we will stop at this point and we will continue in the next session.